All right. This is going to be an interesting one. This topic here is called Euler's method. It is not Euler, it is Euler. And this one here is going to be probably the first section in this class where it's actually like straight up BC material. Okay, we could do this in AB, but it's not that necessary. It's actually not on the test for the AB test, so we don't actually teach it in AB, but it is on the BC test. Okay, so you're going to probably see this probably once or twice, not too many times. I doubt that it's on a free response. Everyone that I've looked at recently, it's not on there, so it's probably just going to be multiple choice. Okay. Basically what's going on, Euler's method is a numerical approach to approximating the particular solution of a differential equation. It uses the concept of local linearity to approximate the shape of the solution curve. We'll talk about what that is. Use the slope of the curve to create short connected lines. So basically what happens is we are going to, let me scroll down a little bit here. We are going to use use a slope at some arbitrary point to create a tangent segment. So, for instance, if this is x sub 0 right there, that's x sub 0 comma y sub 0. Let me do this way up here. Okay, x sub 0, y sub 0. And if I look at that point, the tangent line is actually like this, right? That's the tangent line there. So what happens is that tangent line is going to extend to the next point, okay? And that next point is going to be x comma 1, y comma 1. I'm sorry, x sub 1, y sub 1. And then therefore, if I take the slope of that point, okay, that actual spot there, okay, I'm going to get the next point, okay? So it's going to keep basically going up and up and up, and you're going to see that this basically this local linearity right here that I'm actually making is going to create what looks to be a solution curve that mimics the actual curve of the function, okay, that differential equation there. And so this is x2 comma y2 and so on. If I take the slope of that line, like that's going to even get very big. And these points are arbitrary. Again, it's based on what you're given, okay, and I'm going to give that one, and that's going to be, we'll say that goes up there, and that's this x4 comma, or x sub 4 comma y sub 4, 4 comma y sub 4, and it goes on and on and on based on how many segments you want. Okay, so the length of each segment is predetermined. Okay, it's what we call the step size, and it's either notated as h or delta x. So it's the change. Right, so it's the change in your x values. Okay, so we're going to look at the change in your x values from one to the other. All right, so remember we had h's when we did limits, right? F of x plus h. Okay, that h is the width of your rectangles, or the width of your like step sizes, I guess, if that's what you want to. I guess they're right there, but. The width of your rectangles. And delta x is just another way to say that. So the next segment from x1 to x2, so this segment right in here, uses the slope at x1 to find the next point, right? So the slope there is whatever, and we just follow those particular points up and up and up. So the slope of this point, okay, or this dot here is going to be the slope of this point, x2, and then this value here is going to be the slope of x3. And the process continues until you reach the value that you were trying to find. So for instance, if you were going to try to find f of 1.4 or f of 7 or negative 0.25, like we're going to give you those values to find, and we're going to have to find the approximate value at that point. Okay, it's never going to be exact because it could be either an over approximation or it could be an under approximation based upon what the function is happening, right? So what's the function doing? So this function here is concave up, and it's increasing on its, looks like to be on its domain, right, forever. So that's why the graph is going to look like this. But if it was concave up, it reached a point of inflection, and then it became concave down, then your your local linearity or Euler's method is going to be a little different. Okay, it might not be as exact. All right, so this is kind of what you need to do. So how to find the next point in the process. Okay, so what's going to happen is we are basing Euler's method, and it comes from the point-slope formula. So the original point-slope formula is y minus y1 is equal to m times x minus x1. Okay, so this is our, again, point-slope, right? You've been doing this since Algebra 1, hopefully. And what is going to happen, so the next point, if our first point is x1, y1, then that means our next point, is going to be x sub 2, y sub 2. Okay, x sub 2, y sub 2. So if I take this point here and I sub it in, I'm going to get y sub 2 minus y sub 1 is equal to m times x sub 2 minus x sub 1. And that gives us the next point-slope equation for y sub 2. All right, and then if I keep going, okay, and I kind of want to make a mental note first. So what do I know? This here, x sub 2 minus x sub 1, these points here are always going to be your delta x. Your delta x is always going to be x2 minus x1. And so that's the change, right? That's like the height of the rectangle, or the length of the rectangle, okay? That h piece. So if I want to now rewrite this a little bit, I want to say y2 minus y sub 1 is equal to delta x times m, right? So that's nothing new, so this just subbed in, okay? And so now I want to solve for y sub 2. That's equal to, I bring this over, I get y sub 1 plus delta x times m. But what do we know about m? We know that m is our slope of the tangent line. So I can rewrite that as, so y2 is equal to y1 plus delta x times dy dx. Okay, so times whatever that slope is. All right, and that will give us our y sub 2 value. And what I want to do here is I want to evaluate dy dx at the point, x1, y1. Because if we evaluate the point at x1, y1, that will give us the approximate value of whatever the y2 value is. Okay, that'll give us our slope and so on. And then I'm just going to keep going in order. And so then what's going to happen in order to get to the next one, this is going to be y sub 3 equals y sub 2 plus delta x times dy dx. And we're going to take this value and we're going to evaluate it. Evaluate, there we go. Dy dx at the point x2, y2. So you can see, in order to get the y3, in order to get that approximate value, we're going to evaluate the slope, dy dx, at the previous point, x2, y2. If this is y2, we're going to approximate it at x1, y1. If it's y4, we're going to approximate it at x3, y3. All right, and so on. Okay, so that's basically what we're going to do. That's your general formula for the Euler's method. So in general, let's make a general type of statement here. This here is going to be y sub n is equal to y sub n minus 1 plus delta x times dy dx. Okay? Now, this is your n formula. So like this is, if I want to evaluate it at the fourth thing, then y sub 4 is equal to y sub 3 plus delta x times dy dx. Okay? Whatever that slope is at this particular y sub 3 value. All right? That's your general form for Euler's method. So in general, the smaller the step size, the better the approximation will be. If your step size, okay, if your step size is like 0.7, it's going to be maybe a little bit different unless your step size is 0.2, right? So their values are going to be off by a little bit. That's okay. Again, it's approximation. It's not the exact value. But the smaller the step size, so the closer the step sizes are to one another, the better your approximation will be. And then the approximation will be an overestimate if the curve is concave down. We talked about that already. If the curve is concave up, curves matter, right? Example. Is there 2 examples? Yeah, there's 2 examples. Okay. So, first example. Let f of x, y equals f of x, be the particular solution to this diff EQ with initial condition f of 0 is equal to 1. Use Euler's method to approximate f of 1.5 using 5 equal step sizes. Okay, so I'm going to make a table. This might be the best way to do this. I'm not sure. Like whatever you guys want to do, but for me, maybe a table is probably going to be better. So we're going to make a table. Okay, we know that if x is 0, y is 1. All right, that works out pretty well. And I want 5 equal step sizes. So I'm going to go, this is first step size, second step size, third, fourth, and fifth. So this has to be 1.5 right here. If I want 5 equal step sizes, in order to do that, you're going to take your maximum, you're going to subtract it from your minimum, and you're going to divide by that value of how many step sizes, right? We've done this before with in terms of Riemann sums. Okay, basically b minus a over h, or the amount of n. Sorry, b minus a over n. And n is the number of step sizes. And in this case is going to be 0.3. So I'm going to take and I'm going to go up 0.3. So 0.3, 0.6, 0.9, 1.2, and then 1.5. Great. We know in this case that our delta x is going to be 0.3. That's the step size. The step size is always the values from one x to the other. Okay? So make sure we have that down. So this is 0.3. It's going to be important. Remember our formula is y sub 1. We're going to start with y sub 1 because we want to find out what this value is here. Is equal to y sub 0 plus 0.3 times 0 minus 1. Now, where did I get all these things from? This here is what this is. Y sub 0 is the initial. That's our initial, right? So hopefully we understand that. So this is x sub 0, and this is y sub 0. And then y sub 1, y sub 2, y sub 3, y sub 4, y sub 5. Okay? This 0.3 is our delta x. So y sub 1 is equal to y sub 0 plus delta x times dy over dx. Delta x is 0.3. How do I get dy dx? I'm going to take the values of the point before what I'm finding. So I'm finding y sub 1. I'm going to take the values from the point before, which is 0, 1, plug it into my slope, and that's how I get 0 minus 1. All right, nothing new, nothing crazy. So I'm going to bring that down here, and I get y sub 1 is equal to y sub 0, which is 1, plus 0.3 times negative 1. When I solve this, I get 0.7. Okay, so y sub 1 is 0.7. Now I'm going to use that information to find out y sub 2. So y sub 2 is equal to y sub 1 plus delta x times dy dx. So that's y sub 2 is equal to, y sub 1 in this case is now 0.7, plus delta x in this case is always 0.3 because we had it over here, times, now dy dx, I'm going to use the previous point. So x is 0.3 minus 0.7 from the y value. Again, the slope with the previous points. So y sub 2 is equal to 0.7 plus 0.3 times negative 0.4. And that is equal to 0.58. Okay, 0.58. So this is going to now be 0.58. And we're going to keep doing this iteration until we get to 1.5. So let's go over here. We're going to go, I'm going to not write everything down. I'm just going to write the values and then what we get. So y sub 3 is equal to y sub 2 plus delta x times all of this, right? So y sub 3 is equal to, y sub 2 is 0.58 plus 0.3 times, in this case it's 0.6 minus 0.58. 0.6 minus 0.58. Which y sub 3 is going to be 0.586. Okay? So that's y sub 1, y sub 2, y sub 3. We got to go y sub 4. Y sub 4 is equal to y sub 3, which in this case is 0.586, plus 0.3 times, now I got to subtract 0.9 minus 0.586. which that's going to be 0.6802. 0.6802. 0.6802. And then I'm going to do the last one for y sub 5 there. And that's 0.6802 plus 0.3 times 1.2 minus 0.6802. And I'm going to end up with 0.83614. Okay, so 0.83614. So we're going to say that f of 1.5 is approximated as 0.83614. And so we just used Euler's method to come up with the value of f of 1.5 using this iteration process. All right, using that iteration process. So if you want to try doing the next one, I'll give you a little bit of time to pause. All right, and let's go on to the next one here. So, I know y of 1 is equal to 3, and I want to approximate y of 0 using 4 equal step sizes. So again, I'm going to make my table, and I don't care if it's a horizontal table, vertical table, it doesn't really matter. I just like to make a table because it really just makes life easier. Okay, so we know the initial condition is when x is 1, y is 3. With 4 step sizes, so this is 1, 2, 3, 4. So this is why I want to find out when x is 0. What is our y value? So if I have 4 equal step sizes, I'm going to say it's 0 minus 1 over 4, which is negative 0.25. So then I'm going to go to 0.75, 0.5, and 0.25 are my values. Okay, and now I got to find these y values by iterating that using Euler's method. So Euler's method says y sub 1 is equal to y sub 0 plus delta x times dy dx. Okay, what is our delta x? Our delta x in this case is this value here. So delta x is equal to negative 0.25. Alright, so y sub 1 is equal to y sub 0, which is 3, because that's our initial condition, minus 0.25 times this piece is using this differential equation with x is 1, y is 3. So that is 2 plus 3, which is 5, right? When I do that math there, I get y sub 1 is equal to 1.75. Okay? Let's go to the next one. Y sub 2 is equal to y sub 1 plus delta x times dy dx. So y sub 2 is equal to y sub 1, which is 1.75, minus 0.25, which is delta x, times, now I got to plug these values in for x and for y. Okay? When I do that, I get 3.25. And therefore y sub 2 is equal to 0.9375. 0.9375. Let's find the next one. Y sub 3 is equal to y sub 2 plus delta x times dy dx. So y sub 2 is 0.9375 minus 0.25, which is our delta x. Our dy dx in this case is going to be 1.9375. 1.9375. And when I do that math, again, calculator is 0.453125. Okay, so that'll work there. 0.453125. And now let's find our last value there, which is the value that I actually want, which is y sub 4, which is equal to y sub 3 plus delta x times dy dx. Now you're seeing I'm doing all of this for each of them. You don't have to. Once you get the practice and making sure you know what you're actually plugging in, you're okay to kind of skip some of these steps. That's okay. All right, I'm not going to hold it against you. 0.453125 plus, actually it's minus, let's change this to a minus, 0.25 times dy dx in this case is going to be 0.953125. Oof. Now I know you AP and BC, like you want to truncate at 3 or round to 3. But when we're doing these intermediary steps, you want to go as much as you can handle. 6 is pretty good. If you want to go to 4, 5, or 6, that's great. If you want to go to 9 or 10, fantastic. But try not to stop at 3 because then you're rounding already instead of letting your values kind of do the work for you. All right, so don't round in the middle here. At least go to 5 or 6 places if the decimal has that many places. And then my answer is going to be 2.21484375. So in this case, yes, I can round it to 0.215 or leave it as 0.214, truncate or round. That's okay. But this is what your y of 0 is going to be approximated as right there. All right. Well, it's Euler's method. It's really not that hard to understand. It will definitely let you know that what to do if you have to do Euler's method or whatever. It will tell you what to do. It will you just have to make sure you're following the right iteration between y sub 1, y sub 2s, and y sub 3s and all that stuff. Okay, make a table. It makes it easier on your life, and then use all that iteration process. All right, until next time, deuces.